Hello, my name is Nick Majerison and this is Top Med Talk. And on today's Top Med Talk, we have 5 talks taken from the Xtreme Everest Symposium. They are Chris Imray, Kay Mitchell, David McLeod, Richard Moon and Mike Grocott. And they are talks 5 through to 10 of the Xtreme Everest Symposium. Now, if you go to the podcast show notes, you'll find a link to all 10 of the Xtreme Everest Symposium talks. Have a little look on there and listen to these in their entirety. However, before that, let's have a quick listen to, in highlight form, some of these talks, beginning with Chris Imray, moving to Kay Mitchell, David McLeod, Richard Moon, and then Mike Grocott's plenary lecture. Have a listen.
Top Med Talk.
I have a particular interest in extreme environments, in particular altitude and cold, and I'm trying to summarise in the next 20 minutes or so my PhD, which is 15 years of work, looking at cerebral hemodynamics in man, clinical and applied observations. So I'm going to talk a little bit about history, then talk about cerebral oxygen delivery in particular, neurological effects of ascent to altitude, cerebral oxygen delivery in carotid surgery, something looking at high altitude pathologies, and then end up with some potential translational implications, which I hope will generate interest from those of you who aren't planning to go to altitude shortly. So, just starting back in 1862, we're now in the Midlands, which is where I come from, in the UK. The great fashion, the big advance then, the excitement was going hot air ballooning. And a couple of people, a guy called James Glaisher and Henry Coxwell, took off from the gasworks in a balloon. And they flew up to a total of 28,000 feet, but began to run into trouble. At 29,000 feet, one of them recorded, "I laid my arm upon the table, possessed it of full vigour, but being desirous of using it, I found it powerless." So possibly the first extreme hypoxia TIA. So the brain is an important organ, as I'm sure you're aware, but it's hugely energetically challenging. Although it only accounts for 2% of the body weight, something like 15% cardiac output and 20 to 25% of body oxygen consumption and glucose consumption. Flow is high. Glucose is the obligatory energy substrate with negligible stores. And you can see here on an early PET scan the relative preponderance of oxygen delivery to the brain compared to the heart and the liver. So autoregulation is something that we all learn about, but it's an important thing when we're going to start changing both the PiO2 and the PaCO2. Blood pressure is a key determinant of cerebral blood flow, and it's constant over a long period of time. But you do run into problems either at extreme high blood pressure or extreme low blood pressure. Arterial carbon dioxide and arterial oxygen are the other 2 major determinants. And you can see here at low oxygen levels, so this is what's happening at extreme altitude, you see an increase in cerebral blood flow. And at high CO2 levels, you again see an increase in cerebral blood flow. The problem is that as you hyperventilate at altitude, you actually drop your CO2. So we've got 2 completely different approaches here, where we've got a drop in CO2 tending to reduce cerebral perfusion and a drop in O2 tending to increase it. There are other factors that will determine local flow, and that's local metabolic activity and neural autoregulation. So what happens at altitude? We've talked about the general factors. In the earlier talks, we've talked about hyperventilation, heart rate, and hematocrit, all of which tend to increase oxygen delivery. The brain, however, has some specific ways of coping. It has this very high metabolic requirements, and so there needs to be some way of increasing cerebral blood flow to maintain cerebral oxygen delivery. And you can see here, if you follow the black line here, there's an immediate drop in cerebral blood flow, but this tends to go up over a period of hours and the first couple of days before returning towards normal. The other challenge that you've got with the brain is that it sits within a fixed cranial vault, with a fixed volume. And this means that any swelling that occurs there can adversely affect flow. So although the initial changes may be advantageous, if you then end up with high pressure within the cranial vault or raised intracranial pressure, then you can run into serious problems.
Top Med Talk.
Difficult to talk about epigenetics without talking about genetics first. So I'd like to give you a bit of a potted history of some of what we know about DNA. In 1843, Mendel described Mendelian inheritance, and he talked about dominance and recessiveness in relation to phenotype. And Levine in 1929 introduced the concept of nucleotides. These are the DNA being made up of strings of nucleotides which contained a base attached to a phosphate group and a sugar. And these nucleotides were either adenine, cytosine, guanine or thymine. And Chargaff in the 1940s further refined this, and he showed that these bases were paired up. So adenine is always paired with thymine and cytosine is always paired with guanine. And then we go to 1953, and we've heard a lot about a particular significant event in 1953 in relation to climbing, and this was when Hillary and Tenzing got to the top of Everest, but something else was going on in relation to DNA as well. And during this year, we saw the production of this photograph, Photo 51. And this has been described as the most important photo ever taken. And this is an X-ray diffraction image of DNA taken by Rosalind Franklin. And this photograph supported the announcement by Watson, Crick and Wilkins of the double helix structure of DNA. And these three guys won the Nobel Prize for medicine for this announcement, but Rosalind Franklin was not so honoured. So we know that DNA is double-stranded. You get some DNA from your mum, you get some DNA from your dad. And you can see here this adenine paired with a thymine and the cytosine paired with a guanine, and these are bonded by hydrogen bonds. What else do we know about the human genome? Well, if you stretched out the DNA in a nucleus, it would stretch for about 2 meters, but it's very carefully packed. Most nuclei are less than a micron in diameter. And one of the ways that it does that is you get 147 base pairs, and they're wrapped around these histone molecules in groups of 8, an octamer of 8 histones. And this DNA contains 20,000 genes that code for protein. But those 20,000 genes only make up about 1.5% of the total DNA. So there's about 98.5% of DNA material that we don't know quite what it does. But 99% of our genome is identical across all individuals. So a bit about genetics and hypoxia tolerance. Mike has showed this before. This is the angiotensin converting enzyme gene, and there are 2 alleles, I and D. And in a seed-dwelling population, on the left, there's a normal distribution. But on the right, with the elite high-altitude climbers, the distribution of alleles is not normal. And this is the same with critically ill patients. So if you have a D allele, your risk of mortality if you develop acute respiratory distress syndrome is much higher. So there's an association between having at least one copy of the I allele that seems to suggest that you might do better in hypoxia.
Top Med Talk.
So my title is A Slightly Different Path to Everest. So I am an anesthesiologist and I share that with my colleagues, but I'm not an intensive care physician. I'm much more simple-minded. I perform nerve blocks, regional anesthesia. But I do run the Human Pharmacology and Physiology Lab. And in the conduct of that work, we take healthy volunteers and we expose them to hypoxia to deliberately desaturate them to test equipment, such as pulse oximeters and cerebral oximeters. And in 2007, I was attending the hypoxia meeting at Lake Louise when I encountered Professor Philip Ainsley, who happens to be a fellow Brit. He's also a climber, but he's also an exercise physiologist. And he had just returned from running an expedition to Everest and was giving a presentation at hypoxia. And afterwards, as these things often happen in the bar, I said, if you ever go again, let me know, I'd love to come. And he was intrigued that I was putting in jugular bulb catheters as part of my work. And so a couple of years later, I get a phone call saying, we're going to go again in 2012. Are you interested? And it was an immediate yes. And their focus, they are a group of exercise physiologists who are particularly interested in cerebral blood flow. So I'm going to present the work related to our two expeditions in 2012 and 2016. So as we have heard, is that the human brain, although it's small, it consumes a huge amount of energy in relation to its size. And it obviously requires substantial substrate to do that. And the statement, blood flow matters, is very true. So this is entitled The Red Wing Experiments from the University of Minnesota. And in the 1940s, there was a problem of loss of consciousness in pilots as they were pulling high G during bombing runs. And so they wanted to investigate what was happening. So this is called the KRA cuff, after the three people who invented it. And it's a pneumatic cuff that is secured over the lower third of the neck. And there are inflation pipes, and it's pneumatic. And it rapidly inflates within 0.1 of a second, 600 millimeters of mercury, and instantly becomes an arterial and venous tourniquet. And that stops blood flow immediately. Now, I work in a human volunteer lab, and I have to approach the IRB, and I can't quite understand how I'd ever be able to get this through the IRB. But the investigators, to their credit, actually tested it on themselves. So, what happens when you interrupt blood flow? So, within 3 to 10 seconds, the subjects would become unconscious. And you would think that that would probably be the time to let the cuff down.
Top Med Talk.
I'm going to flip the oxygen seesaw in the opposite direction and talk about hyperoxia, extreme hyperoxia. I don't have any disclosures relevant to this talk, but I'm going to talk a little bit about the history of hyperbaric oxygen, the physiology, and then therapy that is for selected indications, just to give you a flavor of what it's all about. And finally, talk about oxygen toxicity. So hyperbaric oxygen is defined as administration of 100% oxygen at greater than 1.4 atmospheres absolute. Typical treatment regimen is 90 to 120 minutes at 2 to 3 atmospheres, 1 to 3 times per day. This is what we do therapeutically. There's no hip issue here. These are all faked except for the baby, and I don't think anybody recognizes the baby. But oxygen is administered in 2 types of chambers. One is a multi-place chamber, which is compressed with air, and you have oxygen delivered by a head tent, such as in the upper left and or endotracheal tube, lower left, or in a monoplace chamber in which the entire volume is filled with 100% oxygen. So what happens under these conditions? And what you see here are the results from an experiment we did some years ago to look at nitric oxide function under hypoxic conditions, normoxia and hyperoxia. So on the left, you see blood gases. So under hypoxic conditions, the arterial and mixed venous PO2s are respectively about 40 and 30. Under normoxic conditions, the usual 100 millimeters of mercury arterial and roughly 40 millimeters of mercury in the mixed venous. And at 3 atmospheres, the arterial PO2 was about 1,400, and the mixed venous was about 400. So the entire blood system is fully saturated with oxygen, and the organism is basically living off the dissolved fraction. Now, on the upper right, you can see the cardiac output tends to go up with hypoxia, down with hyperoxia. The hyperoxic effect seems to be a baroreceptor effect. So what happens is when you breathe hyperbaric oxygen, you get increased reactive oxygen species that then consume nitric oxide, which is, of course, a vasodilator. And so if you have less vasodilatation around, you get, therefore, vasoconstriction. Blood pressure goes up, heart rate goes down by virtue of the baroreceptor reflex, and cardiac output goes down as well. And then at the lower right, you see the effects on pulmonary vascular resistance. In blue, it goes up with hypoxia and down with hyperoxia, and systemic vascular resistance goes in the opposite direction. It goes up with hyperoxia, so you get vasoconstriction. So that's basically the physiology. The history actually dates back to the 19th century when compressed air work was first designed in Belgium for use in mines. If you're digging a mine through essentially quicksand, you have to hyperbaricize the environment, compress the environment to keep out the water. And this is the first compressed air project in the United States. It was the bridge across the Mississippi at St. Louis, where the environment where the men were working, basically in quicksand, you can see that the surface of the water, and then the next line down is the bottom of the river, but from there down to bedrock is another 4 or 5-fold depth in which it would be impossible to build a bridge in the usual fashion. Basically, what you do normally, you put a cylinder on the bottom of the river, you pump out the water, and guys go down and dig and build the bridge tower. So this device on the right, the bridge tower, underneath of which is a compressed air environment, men would work down there at a pressure that reached the equivalent depth of about 130 feet. And at the end of the shift, it's Miller time, so they would instantaneously decompress, climb up the 10 to 13 stories to the top, and then go and have some refreshment. But many men died. There were 14 known deaths at that time and numerous cases of decompression sickness.
Top Bed Talk.
Situation up here as far as we know it. I can see 1, 2, 3, 4, 5, 6 people on the triangular face, over. So rescue party dealing with a Nepali woman.
Can we just revise that time estimate? The guys have moved really fast. We can see them just over the ice bulge.
High on the mountain, a female Nepali climber, Usha Bista, has succumbed to the lack of oxygen. She has been found by another team, delirious and alone, at 8,500 metres.
We need someone to come in here who speaks. Someone who speaks very good Nepali and very good English. Someone to come in as well. Yeah.
Here was a person on their own, getting into that situation where they get sick, no one with them to realise they're becoming unwell, becoming confused, and the outcome of all that is that she ends up unconscious at 8,500 metres. Not a great place to become unconscious with no one around you.
Mike knows if they don't act immediately, this could be fatal.
What did you drag her on? Stretcher or no stretcher? No, she doesn't. Does she know what day it is? You need to respond. So she's in a tent.
She's in tent.
Whereabout? Summit. She went to Summit.
So I'll leave that there, and we'll come back to Usha's story a little bit later on. But hers was one of the stories that became intertwined with ours as we tried to both climb the mountain and do the science. The image you can see in front of you now, this is Everest from the north side. So as I'm sure you know, Everest sits on the border between Tibet, now part of China, to the north, and Nepal to the south. So this is looking from the Tibetan side. And this is the side of the mountain that was the only side that was approached for 20, 30 years before the war. And attempting to climb Everest was essentially an exclusively British game, because the British were effectively the colonial power, although not in name, they were effectively the colonial power in Tibet. And during the 1920s and 1930s, there were a number of expeditions. I imagine some of you will have read of them or heard of them, of incredibly brave. I mean, the level of exploration in comparison to what happens now is extraordinary. Sadly, all gentlemen in their tweeds and multiple woven underwear attempting to get to the summit of Everest. And although they didn't succeed, they did come remarkably close. So both with and without supplemental oxygen, they came within just a few hundred metres of the summit of Everest during the 1920s and the 1930s. The Second World War came along, nothing happened during the late 30s and early 40s, and then just as people were starting to contemplate climbing Everest again, the Chinese invaded Tibet. Tibet became abruptly closed to any external visitors, and Nepal, which had previously been a very private country that had not particularly welcomed foreign visitors, and when they came had kept them just in the Kathmandu Valley, abruptly opened up prudently to allow visitors to visit the south side of the mountain, and these were the sort of views they got. And there was a reconnaissance expedition in 1951, swiftly followed by a Swiss attempt at climbing in the spring of 1952, where again, 2 climbers got very, very close to the summit but did not succeed. So Raymond Lambert, a well-known Swiss guide, and Sherpa Tenzing Norgay, so Sherpa Tenzing that we'll hear of later, got close to the top, and they probably didn't succeed because they hadn't appreciated the issues around dehydration, and they didn't have adequate facilities to melt water and therefore get liquid. And arguably one of the reasons that the British did ultimately succeed was their attention to the quite basic physiological principles, including hydration and the use of supplemental oxygen. So the Swiss came close but failed in 1952, and in 1953, as you all know, on the eve of the coronation of our current Queen, who is still around, which is just extraordinary, Edmund Hillary and Sherpa Tenzing Norgay succeeded in reaching the summit of Everest in late May, and finally demonstrated that humans could reach the highest point on the surface of the Earth.
Top Med Talk.
Now, don't forget you can meet the Top Med Talk team. All you need to do is go to the ebpom.org website. That's EBPOM, Evidence-Based Perioperative Medicine, ebpom.org/meetings. Get yourself there and you'll find out all of the talks that Top Med Talk will be in attendance at. So that's ebpom.org/meetings. Also, of course, don't forget to sign up for our newsletter. It's a great way of us keeping in touch with you and warning you when we're going to be going live on the Top Med Talk website. If you go to topmedtalk.com, you'll find the mailing list pretty easily once you're there. topmedtalk.com.